Welcome to Lesson 12D, Oblique Shock Reflections. In this lesson, we'll discuss what happens when an oblique shock reflects off a solid wall. I'll show a step-by-step procedure for calculating flow properties downstream of this reflected oblique shock, and I'll do an example problem. Here's what we're talking about. Supersonic Mach number m1 encounters a ramp or sudden change in angle of the duct, producing an oblique shock, which hits the other side of the duct here and reflects. In order for this to work, we have to assume a weak shock and a supersonic m2. Otherwise, if this flow is subsonic, you wouldn't have a reflection. You'd just have subsonic flow from here on. We show our standard notation for the first oblique shock going from 1 to 2, m1 to m2, and we'll call this beta 1, and this angle theta 1, which again, ignoring boundary layers, theta 1 is equal to delta, the angle of the ramp or sudden change in direction. When we go across the oblique shock, we go from 2 to 3 with shock angle beta 2 and angle change theta 2. And note that theta 2 is relative to the direction of m2, this line being parallel to m2. So from the flow's point of view, the change in angle is from this line as the flow approaches to this wall, giving us this theta 2. So a key part of this analysis is that theta 2 is relative to the direction of m2. I note also that in this case, since the reflecting wall is flat, in other words, there's no sudden change of the wall angle up here. So from simple trig, you can see that theta 1 and theta 2 have to be the same. So theta 2 equals theta 1 when the reflecting wall is parallel to the oncoming flow m1. If not, for example, if this wall were tilted at some angle, this would not be true, and you'd have to do a little trig to figure out what theta 2 is. We also know that since the flow has to be parallel to the wall after the reflected shock, m3 is parallel to the wall here. I'll expand this comment as another bullet item, namely that we define theta 2 and beta 2, the shock angle of the reflected shock, relative to the flow moving at angle theta 1 and Mach number m2. In other words, for this oblique shock, we consider the flow upstream of the oblique shock with this turning angle relative to this flow. We'll let this angle phi be the angle of reflection of the oblique shock relative to the wall here in region 3.
Is the angle of incidence equal to the angle of reflection?
No, Freddie. Actually, phi and beta 1 are not equal. The angle of incidence here is not equal to the angle of reflection. In fact, it turns out, again from a little trig, that this angle phi is beta 2 minus theta 2, as you can clearly see here. To help us visualize this a little easier, imagine taking this diagram, flipping it vertically like this, upside down, and then rotating until region 2 is horizontal. I end up with this view of the flow, with m1 coming in at this angle, and this wall and m2 flow being horizontal. And in region 2, this looks exactly like what we've been discussing previously for region 1 to 2, but now we go from 2 to 3, with this angle phi being the angle of reflection off the wall, and beta 2 is relative to the incoming upstream flow, which is how we always define beta 2. So we can calculate beta 2 from the theta beta m equation, but use Mach number m2 since it's the Mach number approaching the oblique shock, and theta 2 since it's the change in angle of the flow. And as we just said, angle phi of the reflected shock is not equal to beta 1, the incidence angle of the approaching oblique shock. We'll use a term that you may have seen before, namely this reflection is not specular. Specular being defined in physics for some waves where the angle of incidence and the angle of reflection are the same. That would be specular. But for oblique shocks, this is not specular. Why? Because the reflected shock is weaker than the incident shock, since M2 is less than M1. Therefore, angle phi is less than beta 1. The non-specular reflection looks more like this, with phi less than beta 1. And I should point out up here that this angle is also beta 1, since these two walls are parallel. You can also think of this dashed line here as an imaginary approaching wall for the reflected shock. Again, this wall does not have to be parallel to the bottom wall, but when it is like this, theta 2 is equal to delta 2, which is also equal to theta 1. That would not be the case if this wall were not parallel to the bottom wall. Now let's discuss the procedure to solve for M, P, T, etc. in region 3 downstream of the reflected oblique shock. Step 1 is to calculate beta 1 for the given M1 and theta 1 from the theta beta M equation. And recall that we must do this implicitly since we're solving for beta 1 in our equation. Step 2 is to calculate the normal component M1n, which is M1 sine beta 1. And I'll actually have 3 subcalculations within step 2. Once we calculate M1n, we can calculate M2n across a normal shock with M1n upstream, as we've discussed in previous lessons, since the normal component upstream of the shock determines the normal component downstream of the shock. We'll use the M2 over M1 equation for a normal shock, but with M2n and M1n instead of the actual M2 and M1. The third component of this second step is to calculate the actual Mach number M2, where we also know from previous lessons that M2 is M2n over sine beta 1 minus theta 1. Step 3 is to calculate ratios P2 over P1, T2 over T1, etc. as needed, again from the normal shock equations, but using M1n and M2n instead of M1 and M2 themselves. I point out that steps 1, 2, and 3 are the same steps that we've used for a non-reflecting oblique shock when the supersonic flow encounters a sudden change in the wall direction. Well, now we're in region 2, and we again have a flow approaching a sudden change in the wall direction, which generates an oblique shock from 2 to 3. So we repeat these 3 steps, but going from region 2 to 3 instead of 1 to 2. I'll write that out here, namely that we repeat steps 1 to 3, but for M2 and theta 2 instead of M1 and theta 1, since it's really just another new problem of an oblique shock formed by a sudden change in the wall. So step 4 is to use M2 and theta 2 to solve for beta 2, again using the theta beta M equation, and implicitly just like we did with step 1. And recall that in our example case, theta 2 and theta 1 were the same, but if we had a different theta 2, we still do this step using whatever theta 2 we have. And I'll now have 2 sub-steps or calculations in step 4. We didn't have to do this in step 1 for the first oblique shock, but now we calculate the angle of reflection phi as beta 2 minus theta 2. Now step 5 is similar to step 2 in that we have these 3 calculations. We calculate M2n, we calculate M3n across the normal shock using M2n, we calculate M3 itself, namely M3 is M3n divided by sine beta 2 minus theta 2, which is the same equation we had above in step 2, except with subscripts 2 and 3 instead of 1 and 2. Step 6 is to calculate the ratios P3 over P2, T3 by T2, etc. as needed, again using M2n as the upstream Mach number. And then finally, step 7 is to calculate P3, and with wise use of ratios, we know that P3 is P3 over P2, P2 over P1, P1. Where we know P3 over P2 from step 6, we know P2 over P1 from step 3, and P1 is typically known upstream. thus we get our pressure P3. And similarly, we do the same for temperature. And I'll point out here that if you're using software like I recommend, you'll already have these steps in your software, so you can copy and paste all those cells or those equations and repeat them here, just changing your variables to 2 and 3 instead of 1 and 2. So that should be fairly simple. Now let's do an example problem. Air flows steadily in a rectangular duct with a sudden contraction of angle delta at the bottom. I give the oncoming Mach number, T1, P1, and delta. We want to calculate all these parameters at 1, 2, and 3, where the shock reflects off this upper wall. Here are our standard approximations and assumptions, but we also assume that both oblique shocks are weak. I followed the above procedure and did everything in software. Students are encouraged to use these numbers as a test case with your software. If you get the same answers as mine, you should have no trouble with the homework. So I'll just list these 7 steps that I outlined above. Step 1, with M1 and theta 1, we use the theta beta m equation and solve for beta 1. I get 34.9 degrees. Step 2, which you may recall had 3 calculations. M1n is M1 sine beta 1. I get M1n is 1.6029, and from the normal shock equation I get M2n equal 0.66756, and I'm reporting 5 digits here to avoid round-off error when we use these values later. For example here, to calculate M2 and to be consistent to 5 digits, I'll also report beta 1 to 5 digits. And using that here, I get M2 equal 2.0585. Step 3, using the normal shock equations and M1n, I get P2 over P1 is 2.8309, and T2 over T1 is 1.3900. Step 4, using M2 and theta 2, the theta beta m equation gives, again implicitly, beta 2 equal 45.334 degrees, and phi is beta 2 minus theta 2, and theta 2 was given as 16 degrees, so the angle of reflection phi is 29.334 degrees. Here are our 3 calculations for step 5, M2n, from which M3n is 0.71421, and from which the actual M3 is 1.4578. Step 6 gives us P3 over P2 is 2.3341, and T3 over T2 is 1.2964. Finally, step 7, P3 is P3 over P2, P2 over P1, P1, and I'll put the numbers in here, giving me P3 equals 669.51 kPa. And similarly, T3 turns out to be 518.98 K. Now I summarize all these answers to 3 or 4 digits. Our 2 betas are phi, Mach number, temperature, and pressure at 2 and at 3. And finally, I'll make a few comments. We notice that beta 2 is greater than beta 1, comparing these. Why? Because M2 is less than M1, and in our example, theta 2 equals theta 1. We can see from the theta beta m plot, where theta is the same for 1 and 2, but the Mach number 1 curve is taller than the Mach number 2 curve, since M2 is less than M1. So you can see from the plot that beta 1 is less than beta 2. My second comment is that phi does not equal beta 1. In fact, phi is less than beta 1 here. In other words, the reflection is not specular. The angle of incidence is not equal to the angle of reflection, as we discussed earlier in this lesson. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.